Okay, in this section, we're actually going to go back and discuss limits again just a little bit, but we're specifically only going to look at limits at infinity this time, which in reference to your actual function, the graph of the function, when you're talking about the limits at infinity, then you're being asked or you're discussing about what's happening at the ends of your function, like to the far left and to the far right. So that's why it refers to here is the fact that it discusses the end behavior. All right, so an example of what this would mean, and I already have everything filled in here just to give you an idea of what this means by limits at infinity. So let's say that you have the function 3x squared divided by x squared plus 1. Okay, if you were to fill in a table here for this particular function, so I have 0 in the middle, and of course then I have x equal 1, x equal 10, x equal 100. And what I've put here is that we're approaching infinity. So that's what it means when you say that you're discussing limits at infinity. That means that your x is going to be approaching infinity. So you could add more onto this table if you chose to. Of course, you can put any number that you want to in, but like even if you went up to x equal 1,000 or x equal 10,000, you could add some more here if you chose. It also shows you as x is approaching negative infinity, so you've got -1, -10, 100. So this would be your x is getting smaller. This would be your x is getting larger. So when you substitute those values in, then what I have here in red on this bottom row will be the values that you would get, or your y values. Now, those big dots, again, there's a lot of those that have shown up this time when I printed off the notes, but these are decimals. So this would be a 2.97, 1.5, 2.9997. So if you start looking at your y values, because if you remember, when you're doing limits, your answer to a limit problem is in reference to the y value. So as your x gets bigger, these are the y values that you're seeing. So what's going to happen is it's actually getting closer and closer to +3. Same thing's going to happen on the left. As your x's are getting smaller and smaller, then the values that you see here in your table are also approaching +3. So it doesn't matter whether you say that you have the limit as x approaches infinity or the limit as x approaches, and my negative sign didn't show up here because of that dot, as x approaches negative infinity. In both cases, they're approaching +3. Now, you'll see in a little while they're not always going to approach the same at each end, but they do a lot of the time. Now, this is just a rough sketch of what this function actually looks like. So based on what we've seen here in this table, as your x's get bigger, what's happening to your y value? So as x gets bigger, your y values are getting closer and closer to the value of +3. I mean, I didn't label this, but this is just 1, 2, 3 along your y-axis. Same thing here with your x's. As your x's are getting smaller, because you're going to the left, your y values that you have on this function are approaching +3. Okay, next I have a statement concerning a horizontal asymptote. All right, the line y equal L. Of course, if you remember, any horizontal line is always in the form of y equals some number. So you have the line y equal L being a horizontal asymptote of the function if the limit as x approaches negative infinity is equal to L, or the limit as x approaches positive infinity is equal to L. So what that means is if you are dealing with limits at infinity, that means you have the limit as x approaches negative infinity, limit as x approaches positive infinity, whatever value this comes out to be equal to is also giving you a horizontal asymptote of that function. And making the relationship here that you're also determining horizontal asymptotes when you're doing limits of infinity is going to be important, especially in the next section. So like going back to this example, if you notice we had the limit here as x approaches infinity is 3, as it approaches negative infinity it's 3. But because this is coming out to be a specific value of 3, if you notice that's where I've got this dotted line, because that's actually the horizontal asymptote of this particular function. All right, here's a couple of properties that just kind of make things a little bit easier for us in just a little bit. Now, you've got a couple of restrictions here as far as what some of the values should be. So with these properties, R is only going to represent a positive rational number, and C will be any real number. So you have the limit as x approaches infinity of C divided by x to the R. So you've just got some constant on the top, just some real number, and if you divide that by x to some power, then this limit at infinity will always be equal to 0, okay? So if your function fits this format, this will be your limit every single time. And same thing is true even if you are approaching negative infinity. All right, so just a basic example here, actually incorporating the property that we just saw. You're asked to find the limit as x approaches infinity of this function. Now, as we had learned before with limits, you would be allowed, and once y'all kind of refresh your memory on how this works, you actually could do this in your head for this particular step, but you would be allowed to break this, break it apart, I guess you could say, and write this as the limit of this term minus the limit of this term. So you're just finding the limit of those terms individually. And like I said, we learned that we could do that before. Okay, property that we had learned before was the limit of a constant is just that constant. So the limit as x approaches infinity of 5 is simply just 5. Now, this is the property that I was just showing you. See, your numerator, see, is just a real number. It's just a constant. And then you do have x to some power. So based on the property that we just learned, this limit is going to be 0. But if you took the time as x approaches infinity, like if you put in 1 and then 2 and then 3 and then 4 and 5, and you just keep increasing your values of x, you know, like if you were looking at it in a table, you would see that those numbers, those values are just going to get smaller and smaller and smaller. And when I say smaller, I mean smaller as far as getting closer and closer to 0. Therefore, here, your limit is just simply 5. Okay, let's look at this one. Now, I've already written a little bit out here concerning this problem. And then I've got some more stuff that we'll fill in, though. All right, we've got the limit as x approaches infinity of 2x minus 1 divided by x plus 1. Again, if you were to like set up a table and just start substituting values in for x, you know, your x's would need to get larger because you're approaching positive infinity. But if you did that with the top, what's going to happen is the top is just going to keep getting bigger and bigger and bigger. Like if you put in x equal 1, x equal 5, x equal 10, x equal 15. Like I said, as you make your x's get bigger, the result is going to continue to get bigger. And same thing will happen on the bottom. If you use those same values, substitute those in, then your x plus 1, your values there are going to continue to get larger. So you actually end up with infinity over infinity, which is considered to be an indeterminate form. Now, we dealt with indeterminate forms earlier when we did limits. Of course, most of what we concentrated on at that point was just 0 over 0. But infinity over infinity is an indeterminate form. So as it states here, when you encounter an indeterminate form, divide the numerator and denominator by the highest power of x in the denominator. So what you're seeing here is you want the highest power of x that's in the denominator. Well, the highest power of x that I have in my denominator is x. So this tells me that I need to divide everything in the numerator and denominator by this highest power of x. So I would have 2x divided by x minus 1 divided by x. So that would be the top. And then I'd have x divided by x plus 1 over x. All right, so if I were to simplify this, of course, what's going to happen with this first term here is the x's are going to cancel out, and I'm just left with 2. Same thing here, x's are going to cancel out, and I'm just left with 1. Okay, so using a property that I had discussed a while ago, you are allowed to actually go in and take the limit of each of these terms individually. So the limit of a constant, the limit of 2 would just be 2. Now, this is the same property that I had just used a while ago because I do have just a constant on the top and then x to a power on the bottom. So based on that property, we know that this is going to be 0. Okay, again, limit of a constant is just the constant. And this is the same property from just a minute ago. That's going to be 0. Therefore, of course, that would give me 2 over 1, which is just 2. Now, what I've also determined in both of these situations, I have determined the limit is 2 in this case. That previous example, the limit was 5. But what I have also learned is that I would also have a horizontal asymptote, okay? And like I said, knowing a horizontal asymptote is going to play a big part in the next section, so that's why I'm kind of going ahead and stressing it. But this is your answer to the limit, but that would also mean that I have a horizontal asymptote at y equal 2. So like that previous example, I didn't write that down, but the previous example would have a horizontal asymptote at y equal 5.